Okay, everyone, ladies and gentlemen, this is the first class of the robotics for fall 2020, San Diego State University. So I'm trying to teach you in simple language the robotics, and we have to deal with too many math at the same time, the Matlab coding. I try to do that so you can see how to implement robotics in the Matlab coding. Okay, so this is ME 532, Introduction to robotics. Okay, so first of all, the most simple robotic mechanism that you every day is using is your hand. Okay, actually this is your hand, that's right. If this is your shoulder joint, okay, this is, here we go, and this is your hand, that's right, and here is your fingers. Okay, in robotics we name it as end effector, guys. End effector. Okay, and obviously these are the links of your hand, that's right, number 1, number 2. But for simplicity, for starting the robotic topic, I'm saying, you know what, I suppose that your hand is very tight and you squeeze in this position, and this is your end effector, that's right. And assuming that in end effector there is a mass, that's right, that you are carrying on. It's a particle mass, is M and the L. If you have passed the vibration course in me or other professors in DSCL, you have seen that this is the name of this is in the vibration course. Yes, it is pendulum. Let me double make sure it is recording. Yeah, it is. Okay, so this is 1 degree of freedom robot. I hope that you know what's the degree of freedom. Degree of freedom, okay? It's a number of independent motion that your mechanism, your machine, your body can do, okay? So, for example, if this is the model of your hand, or say your leg, and here is theta, so you have only can rotate around the point O, say point O, the shoulder joints. And when you're trying to do that, you are applying what? You are applying a torque, that's right, to your what? To your shoulder joint, that's right, torque. You know, the torque dimension is Newton meter, that's right. So this is the simplest robot that you have ever seen in your life, okay? So now what we're gonna do, I'm trying to develop the equation of the motion. How? I taught you in the too many courses, dynamics, control, vibration, system dynamics, that when you're dealing with the rotational motion, you have to bring up which equation? Yes, moment equation. I O theta double dot. So for refreshing your mind, theta double dot is angular acceleration that you have to know from ME220, which is dynamics. This is mass moment of inertia, mass moment of inertia, and this is the sum. This is sum in mathematics, is right, from kindergarten mathematics. This is sum of the moments around point O. And if you remember that you had the class with me previously, the moment equation, this is the moment equation, that's right. Moment equation, okay, is only valid around a fixed point which here is your shoulder joint, or mass center. Okay, only and only if you apply the moment equation around the moving point sucks, you are solving a wrong problem. Okay, so from dynamics, you know that you have to plot the free body diagram. That's right, that we are showing F B D. So degree of freedom is DOF, free body diagram. So one of the forces that acting on the system, assuming that your fingers part is a particle mass, M is mg due to gravity. That's right. From trigonometry, you do know that this length is L sine theta, and this length is L cosine theta. That's right. This is trigonometry from kindergarten. So sum of the moments around point O. Only force acting on the system is gravity. Okay, and I assume, let me make an assumption. I assume that assumption is this. I'm just assuming. Yes. Friction is 0. Mu. Friction is 0 at the shoulder ends. So we discussed this in the vibration class that I'm teaching every spring, that's right? So it is moment of mg around the point O. Force in the normal distance, that's right? L sine theta. So it's equal to, okay, so positive or negative? Maybe you 1 minute that you think about this, because I taught in my classes that I want you also learn about how it is positive, how it is negative. Okay, this positive obviously is negative. Why? Because always I'm saying that you see that you are trying to increase the angle, but the mg is trying to resist the motion. So resist means negative, means that you are losing. That's why you are loser. So it's going to be negative. Its mg is going to, and I'm going to solve it in the inverted pendulum as a robotic system. So if you inverse this mechanism, it's going to be positive. So mass moment of inertia of this particle mass around point O is what? IC, mass moment of around the mass center, plus md squared. That's right. This is from the dynamics course. So this is the particle mass based on definition in dynamics. So because particle has no dimension, so this IC around the center point is 0, and the D based on the parallel axial theorem that is going out of the page like this, going out of the page. This is the tip of the arrow. So there is the normal distance between the parallel axis. That's right, which is L. So this is equal to L, your D. So it's L squared and theta double dot. So what we're gonna get is ml squared theta double dot is equal to minus mg L sine theta. With this m goes to New York, this L, one of these two square, one of them goes, and finally what you get, for God's sake, so theta double dot, I'm moving this side, gonna be g over L sine theta. This is the famous nonlinear equation of motion of a pendulum. That's right. So obviously we have seen this in the vibration course, but now you know that this is a very simple robotic mechanism. That's right. So we have like this, right? We know that. Let me see, it's recording. Yes. Okay. So this theta double dot plus g over L sine of theta is equal to 0. But I want to control the system. That's why I apply the external torque here, guys. So here, because I'm going to go to Matlab, here the only force is not the mgl, so you're going to have, because tau is helping the motion, see the direction of the arrow, so it is tau minus mgl. So here you're going to have tau. Okay, this is not vibration course, this is the control course, so I want to control it, that's right. So it's going to be tau here, and now the same here with tau minus mgl, and you're going to have a tau here. You got it? Okay, so this is nonlinear equation of the motion. So, but as you know, we can use Taylor series expansion, as I taught in the vibration course, that you can approximate a nonlinear function around this equilibrium point, given that is x naught is the equilibrium point plus round f over round x at the equilibrium point, that's right, x minus x naught, this is from high school, plus round square f over round x square, again as x is equal to x naught, x minus x naught square. But after this is trash, we don't need that. Why? Because we are linearizing, we only need the power 1 of the x, order 1 of the x, right? So by having that, you can approximate the equation of the motion of the 1 degree of freedom robot around the equilibrium point. So as I taught you previously, what's the equilibrium point of the system? Other courses, this 1 degree of freedom robot. So you have to remove tau, and what we're gonna have, because you have to have free motion of the system. Okay, this is how you can find the equilibrium point of the system. Okay, the external torque, we don't have it. So equilibrium point, as its name implies, means the system is in the rest if we do not apply any external force or an external torque. This is definition of simply equilibrium point, means that if you do not apply any external torque or force, so system gonna remain rest. So remains in rest means there is no velocity of the system, there is no acceleration of the system, there is no angular velocity of the system, there is no angular acceleration of the system. So based on what I'm saying just right now, there is no angular acceleration of the system. So the remaining is that sine of theta is 0, which is k pi from trigonometry, and the k can be 0 plus 1 plus 2 and to the end. That's right. So now you have to judge. You have too many equilibrium points for this 1 degree of freedom robotic system. That's right. But you have to select a proper one. Okay, so let me start with the k0. If I say that sine of theta is 0, that's right. I mean, sorry guys, I'm getting older. Sine of k pi. I mean, okay. So if that is 0, it is equal to k is equal to 0. Okay, so it is equal to, let me look like this, k pi. So from here, theta is k pi. That's right. Oops, k pi. So saying k is 0, you're gonna get theta 0. So this is your equilibrium point of the system. We typically show the equilibrium point by star in control theory. Okay. So what about if I say k is 1? So if I say k is 1, theta star gonna be pi. If this is valid, let me know. Look at the graph, okay? This means this position. So if you release, okay, this at this position, what's gonna happen? It's gonna rotate. It never stays there with no friction. Okay, understand? So the system becomes unstable. So This is not valid for your system. Okay. So on the other hand, the equilibrium point for sine theta is 0. So if you, I'm gonna just skip that. If you use that, you can say that sine of theta is theta, cosine of theta around the equilibrium point of 0 is 1, and the tangent of theta always is theta. That's right. So now you have two versions of the equation of motion of 1 degree of freedom robot. Theta double dot. Oh, I forgot to do this, guys, because I'm dividing everything by L. Okay, by L, both sides. Remember, I divide everything by both sides because I changed the problem from vibration to robotics and control. So theta double dot plus G over L sine of theta is tau over L, and theta double dot plus G over L theta is tau over L. Here we go. Okay, understand? So this is a nonlinear equation of motion of 1 degree of freedom robot, and this is linear equation of 1 degree of freedom robot. So I'm pretty sure you have seen this several times in the course of vibration. Now let me go to the Matlab. Okay, this is Matlab. So I want to see what's the difference between this and this, because eventually when you become a robotic engineer, you have to know how to design controller for the robotic system and what is the effect that you apply that for the linear system or for the non-linear system. Okay. Yes, recording. Okay, guys. So when you open the Matlab, I want to say this. You have to open a new script, M file, right? Here we go. Okay. So I'm using the ODE, that's right. So function, because this is ordinary differential equation. These equations, guys, look at here, they are ordinary differential equation. That's right. If you don't know, let me for one time teach you that you have to define state variables and the state space equations. So you're going to say theta is m1 and the angular acceleration is m2. Having the time derivative from the both sides, you're going to have dm1 is equal to theta dot is equal to m2, right? And dm2 is equal to theta double dot. So what is the double dot? You have from here is equal to tau over L minus G over L sine of theta. What is theta? Is m1. So now the name of these, let me now delete this and this, because the name of this is state space equation in Matlab. You have to know coding in Matlab. If you don't know how to code and make simulation and make control in Matlab or Python, robotics, you are not engineer. Okay, simply. Being an engineer doesn't mean that you can develop the mathematics. Being engineering, that means that you can apply it in a real system. Okay, you have to be very clear about this. Okay, so this is nonlinear differential state space equation. The linear version gonna be. So on the other hand, I'm gonna develop. Let me write it here because you're gonna have questions how that happened. So you have one two state variable, 3, 4, because I'm making for the linear equations, right? So that's why I'm writing here when I go to Matlab. Okay, guys. You have to know the skill of the coding at the same time. Okay. So see, so you have 4 state variable. dm1 is equal to m2, and the dm2 is equal to tau over L, this is the control torque, that's right, minus G over L sine of M1. And because I'm making for another, I want to make simulation at the same time. dm3 is equal to M4. This is for nonlinear robotic system, nonlinear, and this is for linear. And dm4, okay, it is, look at here, I have only theta, not sine of theta. See, compare this. So it's tau over L minus G over L M3, because see, okay, this is the angle. This is for linear pendulum or 1 degree of freedom robot. Okay, now I'm exactly typing this here, guys, so you know that. So function is dm is equal to, say, robo, you can say whatever you want, time as that we're typing as t and the m, right, and the m, then length of that robot or the pendulum, that I'm going to say 0.5 meter. Obviously g gravity is 9.81 meter per second square. And now dm, I'm making the state space for that zeros, 4 and 1, right? Let me look at it. Zeros, as if you pass the ME202 the Matlab course with me, it's there, so it makes the 4 zeros, right? So now dm1 is equal to m2, you got it. dm2 is equal to tau, I'm writing, divided by L minus G divided by L multiplied by sine of M1, exactly as I type in the PowerPoint version. This is for the nonlinear. You can even comment that, that's right. This is for nonlinear 1 degree of freedom robot or the pendulum. So dm3 is equal to m4, and dm4 is equal to the same. So except here we go, there is no sign anymore, right? And bear with me, guys, you cannot linearize the 5 degree of freedom robotic system around the current point. It's gonna be funny. I'm gonna explain later. We have too many mathematics before going there. So this is for linear 1 degree of freedom robot or pendulum, right? So now what is tau? Tau is a control torque. I'm gonna teach you if you have time at the end of this semester, okay? So now accept from me tau. I wanted that tau is a periodic signal, sine of t, with the amplitude of 0.2. You get it? So I'm saying that I want that okay, before saving this, let me go here. And I'm telling you that, so I want that apply torque that this bounce like this, right? Ding, 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 ding. Okay? This is what this is that your robotic arm is doing when you are dancing, actually. So now having this, now when you are saving this, exactly the M file name, as I taught a million times, must be exactly the name of what? Let me go to desktop first, and new folder, and ME532 robotics. Okay, must be exactly the name that you typed here, guys. Look at here. Oh, look at here, guys. This robo must be exactly this. If you change it, done. Now after doing this, I'm saving another. So the capital T means the total time, or Y or Z or payment, whatever you want to name it, is equal to ODE 45, ordinary differential equation type 45. Don't accept from me why 45. We have many types of that. 15S, 45, 113, 113S. You have too many solvers, okay? This is not the class of the numerical approach, okay? But 45 is good for the system. So then at in Matlab, as may you know, is calling the another M file at robo, okay? Now I'm giving the time interval between 0. time step of 0.1 to 10, okay? And you have four state variables, so you have to have 4 initial values, 0, 0, 0, 0. Okay, here we go. Got it? You can type this here. Now you can now save it as, I don't know, solver of 1 degree of freedom robo. Okay, and in these notes, no, where was it? Oh, here we go. In this, that's right. I'm saving that here. Okay, and solver and the main file must be at the same folder in Matlab. If you don't know, if you don't have it the same folder, you're done. Okay, now why I did this, because I wanted to compare the linearized version of 1 degree of freedom mode and the nonlinear version of that and linear version of that. So I'm gonna now plot it. Figure 1, okay, plot total time, Y capital, all rows and the first column, multiplied by 180 divided by pi, because it gives you in the radian. You have to change it to degree that it gives you better visualization. That's right. So, and because Y1, because you want to see the first angle, M1. The second angle is gonna be M3. That's right. So, and T the same. That's right. This is Matlab coding, and it's gonna be 3. That's right. So this I'm gonna say put it blue. I'm gonna say this plot me red. These are Matlab codes. You can go to my Matlab YouTube links that I uploaded in the summer 2020, and you can get from there. Get it? And the grid. Okay. Hopefully, if I run it, we'll have the response. Change folder. Okay, you see guys, the difference between linear and nonlinear for 1 degree of freedom mode in this specific problem, guys. Don't judge generally for any system. Oh, I want to see, I'll zoom in. See, it's very negligible, guys. See, it's very negligible. Its difference is, say, give me a number. It's almost 0. Okay, is 0.05 degree. Okay, see, when you're controlling the system, this is not controller, by the way. I'm just giving the external torque. Okay, the control is different subject I'm going to teach you, hopefully. Okay, but you see that for the 1 degree of freedom robot, between linearization and non-linearization is negligible. So now you can see this. So we have another approach that we name it as the phase portrait in Matlab. What is that? This is make it this comment. Okay, and I want to plot the angle versus what? Versus angular velocity, M2 here, because look at here, guys, M1, M2. M1 was position. Look at the notes. Got the note. Here, m1 was the position, m2 was angular velocity. That's right. So, and now here we are, and now and it's going to be 4, m3 and 4. That's right. So the name of this in the literature of the control is phase growth rate, guys. I'm eliminating time from your plot. You see, this is look like very interesting. That's right. Has too many meanings in the nonlinear dynamics and control. This kind of the plot that we name it at the phase growth rate. Okay. So, and if you continue the time, it's gonna evolve. Let me look at here. Let's look at here, guys. It's gonna say I don't know 50 seconds. Okay. What the hell happened? Okay. See, it's gonna evolve. So because it's periodic, you see a regular pattern. I don't want to discuss about this intermittency or whatever it is. Okay. So it's a regular pattern that you see, and very interesting. That has a very interesting topic in nonlinear dynamics. So the field of dynamics and robotics and control, they are like as the loop of a chain. So you cannot separate from each other and discuss them. Okay, understand? So these are all things that you have to know. So this is the angular velocity, angular position, and this is the angular velocity y-axis. Understand? This is how we simulate it. But guys, again, don't misunderstand what I'm saying. I'm not saying that you have to linearize the robotics equation of the motion around the current point, because as you will see eventually, the equation of the motion of a robotic system is going to be very coupled and nonlinear and time varying. Okay, and so what I'm talking about, this is these equations, and this equation is LTI system. I'm teaching ME 696 this semester, linear time invariant system, because the coefficients of this equation are constant. Okay, if the coefficients are constant, you're gonna have LTV, linear time varying systems. So the real robotic system I'm gonna teach you, they are time varying system, not linear but time varying system. Okay, so this is linear time invariant system. Understand? So this was very simple. Let me see. Okay, so this was let me go to the new page because I need space. This was very simple version of the robotic system, super simple robotic system. Okay, so let me go to another a little complex robotic system, guys. Okay, so so let me derive the equation of the motion of your real hand. Right, this is link 1 and the link 2 and the end effector, right, and the end effector. I assume that you have an end effector. I'm assuming the mass of this link of your hand as a particle at the end of that, like this, m2, and the mass of the link 1 of your hand as a particle mass as m1, and this is L1 and L2. This is a realistic sample of your model of your hand, right? And this is a 2D of freedom robotic system, guys. So because it has two independent motion, θ1 and θ2. That's right. So it is a 2 degree of freedom robotic system. That's not what I'm talking about. So sorry for the noise, guys. Some Mustang is leaving the parking probably. Okay. So now I want to show you why you are in this class by this example, and why you need powerful tools and not sticking to the classical approach Okay, so one of the methods that I can solve this equation is this. We name it as Lagrangian equation for the open chain robotic system. What is that? Lagrangian equation is time derivative of round L Lagrangian function over round Q dot K minus round L over round QK is tau control torque K. So suppose that I'm applying it to control torque to the shoulder joint of your hand as a robotic system, tau 1, and here, yeah, tau 2. Now I have to teach you step by step each of them. Okay? So Laplacian is defined as sum of, if you have a robotic system composed of n link or n degree of freedom system, is sum of the kinetic energy I from 1 to K, okay, to N, okay, Tn, minus sum of the potential energy from I1 to N, and this is N. This is definition of the Lagrangian function. Okay, and this QK are the number of degree of freedom. So here you have theta 1, so you can say it is general coordination. So K1, Q1, right? And theta 2 is Q2. So Q dot means theta dot 1, theta dot 2. Understand what I'm talking about? You have 3 degree of freedom robotic system, you're gonna have Q1, Q2, Q3. If you have 10 degree of freedom system, you have Q1, Q2, Q3, Q4, Q10. Example, let me show you. I have a dynamic system and control lab at San Diego State University that I'm experimenting too many things there, guys. What the hell is that? Here we go. Okay, if you go Peimannm.sdsu.edu, this is my robotic system. This backset that you can see here, that we did the deep learning on, that is 7 degree of freedom system. Means that you have 7 general coordinates of the system, Q1, Q2, Q3, and Q7, right? So it's 7 degree of freedom system. Or these nows, they are 25 degree of freedom system. It's very similar to human body because they have legs at the same time. But this is only manipulated. I'm just running one of them to see. We implemented the model-based elastic controller on the Baxter. Pick up an item and pass over the obstacle and put on the destination. See that? Okay. Even implementation of this control system under a real robot system is very challenging with respect to too many things: computational efficiency and interface between the code that you are developing and the real robotic system. Okay. You can go and look at whatever, and we are publishing too much in the robotic systems. You can go and see what's going on. Okay. So now let's go to our topics. So on the other hand, in this system, because you have 2 degree of freedom system, you're going to have T1 plus T2, and here you have potential 1, potential 2. Okay, but because I assume that the mass of this link is at the end of this, and the mass of this link at the end of this, you have to be very careful. Okay, so by definition, let us see what is T from dynamics. For when it comes to the robotic system or the dynamical system, it's going to be 1 over 2 Ti, gonna be mi vci square. You have seen this in dynamics. Means the mass center velocity square plus 1 over 2 ii, which is what this is. You're gonna see eventually this when I reshaping these for a complex robotic system. Okay, ii omega I square. Okay, understand that? So this is mass moment of inertia, and this is the angular velocity of that link of the robot. Understand? Okay. So on the other hand, for each of these, you have T1 and T2. So, for example, for T1, okay, you're gonna have T1 is equal to 1 over 2 m1 is m1. Velocity of this particle mass square plus 1 over 2 I1 omega 1 square. Understand? And you have to do the same here and find the V's and the potentials and too many things. Side 1 over 2 I2 omega 2 square. Understand? And this is with respect to the coordinate system that I attached to the links. So you have, if you have 3D graph freedom system, you're gonna have huge calculations. That's why you need a classical approach for robotic systems. Understand what I'm talking about? Okay. So this is the first class, so I'm stopping here. Okay. And the next class I'm gonna enter to classical robotic system. Just wanted to let you know that we're gonna back to this, but in a very classical fashion. Okay, that you have to know about the Jacobian metrics and how to calculate the total end effector, the angular velocity, and too many things. At the end of the course, we're gonna back to this. But if you do this by hand, you have 7 graph freedom robot, good luck. It's gonna take you 2 months to do that. So you need a classical method of the robotics to generate the equation of the motion and then implement the controller to the system. Okay.